solution is as nice as you could hope for. I mean, the domain is as nice as you could hope for. So the boundary is algebraic. So it's the image of the unit circle by a rational function R, some rational function. There's a similar result also in the multiply connected case, but then the boundary is algebraic, so it's a zero set of a polynomial of two variables. But I will not discuss about this multiply connected case, but there are some results we have also on that. Okay, so it's kind of strange because you usually use quasi-conformal mappings to map something very singular, like the snowflakes or different kind of very strange objects. And then now you have these maps and you make it even ellipticity degenerate on the boundary. So you think that all kind of bad things will happen. But it turns out that in the end, if such a solution exists, then the domain is extremely good. Okay, and how would one prove this kind of result? So this actually proof came out of this study of this random structure. So it's not something that you go home and try to do, but it somehow came up from these random structures. And here I just start with this result. So first, if we have this kind of solution, which is so proper map on the domain, then let's first take a homeomorphic solution to the equation where the coefficient, the Beltrami coefficient is now the same as in our equation here. So the f itself. And here, because the equation degenerates on the boundary, so one has to be a little bit careful to find this homeomorphic solution. So what one does is one gives a complex structure for this domain omega, so that these maps on this structure are solutions to this equation. And then we know that this complex structure can be realized by a simply connected domain inside the disk or the whole plane. And because we have one bounded solution, this F, so this domain must be the disk. The complex structure is the structure of the disk. Okay, so that's the first step. And then, because F, our given F, satisfies the same equation as this homeomorphic solution, we know that we can represent F as a composition of some analytic function and the function G. And because F is proper, also the analytic factor is proper. So we have proper analytic function from the disk to disk. So it's a Plaske product. Okay. And now we have this Plaske product, and then we have this homeomorphic solution to the equation. And then we look at the equation satisfied the inverse of this homeomorphism. So here we have the inverse, and by the usual rules of the inverse of for the equation for the inverse mapping, we have this equation satisfied by the inverse, the mapping G. Okay, but this suggests that we should look at this following expression. This is gamma, and it's a G plus B times the conjugate of G. But because our equation here, the gamma is just by derivative, it's analytic function. D bar of gamma is 0. And so we have two analytic functions. We have the B and the gamma. And it's already a lot of information. So let's make use of that. So here's our gamma. And then now we write it in terms of G and B. And of course, we can make a equation for the we have equation for the G and its complex conjugate. And we solve there I did something strange with the B. Okay, now. So we can solve the function G from this equation, and here's the result. And this holds in the disk where the function g is the homeomorphism g is defined. Okay, but now we know that this homeomorphism was a boundary. I mean, it's mapping from the disk to our bounded domain omega, which we are studying. And because this is bounded, when we go to the boundary, this term blows up. So it means that this other term must go to 0. So we have this relation for gamma and the Blaschke product. But then, okay, that means that if you look at this function gamma at 1 over z bar and the complex conjugate of that equals the gamma over b on the unit circle. But this is a meromorphic function, that's a meromorphic function, and we have a meromorphic function in the whole complex plane. So it's a rational function. Okay, and when we tie this up, it turns out that we can write the original function g in terms of this function of 2 variables. It's a rational function of 2 variables. From these identities, we have for this equation here, we have the representation for the function g. But on the other hand, the g was a parameterization for domain, which we were studying. The one domain which had this supported the proper solution of the Beltrami equation. So it means that the boundary of our domain, which is the image of g on the unit circle, is a rational function because this fellow here is rational. So that's it. It follows that the boundary is an image of a rational function under the unit circle. So extremely well behaving. And we also know something about the geometry of this domain. So all singularities are either first order cusps or tag nodes, and then it's locally convex outside those. So maybe I can draw a picture. So our domain omega, it looks something like this. Let me see if I can. Something like this here are cusps and tag node, and no other singularities. Okay, and also the function f has some strange properties. So it's very singular on the boundary. It's lib 1/2 in almost everywhere. And at the some cusp points, it's like lib 1/3. So it's but this is precisely, you cannot make this any better. So it is this regularity is the optimal regularity. Okay, so we have an equation with very unexpected, interesting properties. So how to find this, or where this equation could appear? So let's then start to look at that, how to arrive this equation, how to find examples of this equation. We had one in the disk, but that's not too much information. So how about other domains? Well, somehow, of course, one should look at suitable PDEs to find these solutions. And then PDEs are typically or nicely here connected with the variational problem. So let's look at the variational problem that will lead to our mappings. So I will look at strictly convex energies. And then I look at the variational principle where the energy is, the sigma is strictly convex, and we are minimizing the energy with given boundary values. And these kind of equations are well known to be related to quasi-conformal mappings, Beltrami equations. So that's why I started this way. Okay, so if the solution is C1 function, then I can get the Euler-Lagrange equations, and from there I can look at the Cauchy-Riemann or the conjugate function of the solution, which is V, and then that satisfies this equation in terms of the structure function sigma. Okay, but then what we do in the quasi-conformal world always that we have the solution and it's conjugate and look at this function f. And I put here 2 because I want to use mix the complex notation and the real notation. So then I don't have extra terms anywhere. So with this definition of the harmonic, I mean the conjugate function, and then this quasi-regular fellow, we see the derivative of the set derivative of the function is this expression here, involving the energy and the solution H. And then the fz bar for this function is given by this structure function, where the structure function is given by this formula on the right. And this, of course, well known. This holds for any let's say monotone structure function for any related PD. So this is well known. But now, so we are looking at this universal Beltrami equation, and what we have here is this equation. So it looks a little bit in the right way, but it's not what we precisely want. You have to do something about it. And like you know, the holomorphic invariance on quasi solution of the Beltrami equation. So we would like to derivate this equation. Then maybe we get closer to the universal one, to this one. Okay, so the next question is that to derivate this, when is this structure function when is the structure function complex analytic? If that's complex analytic, we can derivate it, and then we get four equations of this type, this universal equation. Properties with equation which look like the universal equation. Okay, and this question was studied by Paul Levy in the 30s. He used it some minimal surfaces, but I haven't seen this issue in quasi-conformal literature before. So somehow it has been somehow outside our studies, but hopefully now we can use it more. So our next theorem is that, so once you ask the right question, then the answer is not difficult to get. So this is mainly by chain rule and some calculations. So like here I take this strictly convex energy, and then my structure function is given by this formula. And then my question is that when is this structure function analytic? And answer is that it's analytic precisely when the energy satisfies the Monge-Ampére equation. So it's if and only if. And that's why the Monge-Ampére here comes to the play. That guarantees the analyticity of the structure function H. Moreover, if the first condition here hold, then I will look at the derivative, because I want to derivate the previous equation to get to the universal one. So I need the information of the derivative of the structure function H. And it turns out that it's precisely this expression here. So Laplace of sigma minus 2 divided by Laplace of sigma plus 2. So it's less than 1. So certainly this H prime gives us a function from the domain that's defined to the unit disk. But we want to proper map, because that was the whole point, to have proper maps. So build solution proper maps to the proper solution to the Beltrami equation. Okay, so in what kind of domains this would be this would converge to 1 when we approach the boundary? Well, it's clear that I mean there are this regularity theories for Monge-Ampére equation, and if you had somehow strictly convex boundary, then it will be smooth up to the boundary, and that's not good. But so if you look at look at the Hessian. So here the product of singular values is identically 1, and here we are looking at the sum of the principal values. So if the product is 1 and one singular value goes to 0, the other goes to infinity. So, and that's precisely what we have to assume. So we must have boundary values, I mean, where this principal value goes to 0 for the Laplace. So that means the first derivative is constant, or the boundary value is affine. So that says that we have to look at this Monge-Ampére equation with affine boundary values. That will give us the blow-up, at least on the boundary, these phases. But analyzing the situation more shows that actually also in the corners it will go to infinity if you have piecewise affine boundary values. Okay, so that gives us the framework where we have to stay. So we look at convex polygons, convex function sigma in these polygons which are piecewise affine on the boundary, and then satisfy the Monge-Ampére equation, and they then will blow up on the boundary. And here's an example where here the polygon is the square, and the sigma is 0 on each of these boundary intervals. And then the way, I mean, here's the picture image of this sigma, which is called the amoeba, this surface tension. And it turns out that the sigma, it blows up at this flat point. So this whole side, it maps to infinity in here, in the same direction orthogonal to this side. So this side is mapped to this direction. And then the curves in between, they come from this, sorry. I'm still, okay. So they come from when you approach the square by different angular directions. Sorry. Each direction here corresponds to one point on the boundary, and different boundary points correspond to different angular directions for the gradient sigma. And that's how we get this one example of our surface tension. So any questions at this point before I go? So you remember how the formula for the structure function H. So from I will look at this expression, which I call Levy transform in honor of Levy's studies in the 30s. So from the formula of the structure function H, you get immediately that we have this equality. And this is very interesting because we showed that this H sigma, this is complex analytic, and this omega bar, this is anti-analytic, of course. And then when we put this term on the left-hand side, we see that the inverse of the Levy transform is harmonic. And that's very useful because this somehow combines the structure of the surface tension sigma and its properties very well. And we know that inverse of this mapping is harmonic. On the other hand, because sigma is convex, this is a monotone function, strictly monotone, so this is invertible homeomorphism. So we have nice, interesting homeomorphism whose inverse is harmonic mapping. Okay, so here let's collect what we have. So you have the strictly convex polygon, Monge-Ampére equation there, and piecewise affine boundary values for the sigma. Then we look at the solution to this corresponding equation, the minimizer equation, the minimizer satisfies. Then we look at this complex conjugate, I mean this conjugate function. And here I forgot the number 2, but there should be 2 in this F is 2h plus IV. Then we recall that the complex derivative is given by this expression, which is our Levy transform. And here I recall the formula of the Levy transform. And the equation satisfied by this f, also the derivative, so the minimizer, it is given here. And this is our structure function, which is now analytic under the assumption on the Monge-Ampére equation. And now because the f here, I mean, this h is now complex analytic, so now we can derive it once more. And we get for the, and we assume that the minimizer h is C1, so we have, I mean, for it's even C2 in under these assumptions that this solution of the Monge-Ampére equation. So it's locally well defined. This f is also C1 function, and soon we see it's much more. Okay, but when you derive this equation, we get for the complex derivative, we have this equation here. Where now this h prime is complex analytic, and now we can remember the invariance of the Beltrami equation and the post-compositions with the complex functions. So we see that this function here, this composition of the structure function, derivative of structure function, composition that with the Levy transform, that gives our solution of the Beltrami equation. But there's still, okay, one step we have to settle, and that's when is this solution proper? Because that's what we want, otherwise we don't have anything interesting. So we have this, our function here, which is composition of the structure function h, derivative of the h, Levy transform, and the minimizer or the solution f, h. Okay, and now question is, when is this function f proper map? Well, from this composition, the Levy transform term, that's homeomorphism, because it is monotone function. So that's, I mean, I forgot to, okay, sorry. I forgot to discuss the domain of the H. So what's the domain of H? That's where this expression is well defined for which omega, but that's the image of the Levy transform from the domain of sigma. So that's where the Levy transform, in our example, it was the square. So we know that this Levy transform is from the domain of sigma, so the polygon, to the domain of H, to this amoeba. It's homeomorphism, so it's a proper. Then we know that by this Monge-Ampére equation, this H prime is a proper map from the domain to the unit disk. So those are proper. So that's also good news that maybe that this will give something. But of course, in the last term, the solution H, this can be proper or can be non-proper. I mean, that varies. We have different solutions, the different situations, different boundary values. So the structure functions for the equation, they are proper maps, but the solution, that can be or may or may not be proper map. So we need to look at those situations which are described by cases where the solution is a proper map. And that takes us to these random tilings and timer models and their scaling limits. And okay, so I have some, how much I have? 20 minutes, okay. So I am here illustrating this with many pictures, and none of this picture is made by me. So I have freely borrowed here and there. And so these are those who have been making those pictures. Okay, so random tiles. So if you look at the square, we tile it with this domino tiles. So they can be randomly there, and there's no structure, except uniformly random. But if you twist the square by 45 degrees, you will start to see in simulations this kind of behavior. Some of the corners get somehow frozen, that there's with big probability there's only one color. And this phenomenon was observed in the 90s by people working in integral probability and related topics. And they wanted to understand this phenomenon, why this happens, and what kind of corners you get, and so on. So this is some other also what we want to now study. So here this for Lorentz tile with these three different tiles, and we have hexagon tiled by the Lorentz tiles, and you have here the same kind of frozen corners, 6 corners. And then we take a scaling limit with full probability of probability 1. This kind of phenomena happens. And this is a scaling picture in the scaling limit picture. And this was shown for the hexagon by Kohn, Larsen, Prop in the 90s, late 90s, if I remember correctly. And then somewhat later, okay, 2000, Kohn, Kenyon, Prop, and later Kenyon, Okunka, Sheffield, they showed that if you have any diameter model and you take in a bounded domain, and then you take scaling limit, so then almost surely you have a liquid domain, and often also the frozen boundary, which is somehow ordered part. And then the question became that what is the geometry of all frozen boundaries? This is the question we want to apply to quasi-conformal theory and understand the geometries. Here is again a square, and here is a bit more complicated polygon. And then these different colors, they represent these different. Okay, I'll talk about later these colors, how one should interpret them. So, but anyway, like here you see the color is tells which kind of tiles. So here we have. Okay, sorry. The color tells that which kind of tile we are using, and which kind of tile is frozen in that corner. Okay, but so a little bit discuss diameter models, because I don't know if everybody's familiar with those. So there are perfect matches on a bipartite doubly periodic planar graph. So like here, you have the z squared, and it's a perfect matching. So every vertex is I mean, there are this, every other vertex is black, every other is red, and then we take some matching. So we take pairs these vertices, and that gives us a tiling. So tiling is equivalent to perfect matching. Here we have a diameter model for the lozenges, and we have hexagonal lattice, and here perfect matching for this in the hexagonal lattice case. And then one has machinery to study them, these objects. And then one of the big first results, well, there are many results, but we have the very famous ACTA paper by Kenyon and Kunkov that for Lorentz tilings, the free boundary, I mean the boundary between the frozen and the liquid part, this is an algebraic curve. And that's okay, somehow starting to smell that maybe we could use our machinery here too. And actually, this was what our work started with. We wanted to understand this Kenyon-Kunkov theory from the quasi-conformal point of view, and you use our machinery there. Okay, so to describe scaling limits and to have properties for them, we need some concepts. And what we use here is the Thurston discrete height function. So this height function tells that so you have these pairings, and if you go along the dual lattice on the sides, the edges of the tiles. So let's say if you start here, let's say you go down if okay, so you go here, you go up if you have red on your right, and you go down if you have black on your right. So here, first I go up, and then go down, then I go even more down, and then I go even further. So going along these sides by this rule gives you a height function. And let's say at one point here you take the value 0, and then look at the height function divided by this rule. And that describes precisely the combinatorics of given tiling. So each tiling has a height function. And then what you can do, you can take the asymptotic height function. Namely, you take this tile smaller and smaller, look at the scaling limits, and then the discrete height function has value in the corners of this polygon. But then the scaling limits have values in the big closure, which is the weak limit. Asymptotic height function is the weak limit of these discrete height functions. So it will have values in the closed polygon, not anymore in the corners. So we have a gradient constraint for the height function, this asymptotic height function. Its values should be here in this polygon. Okay, and then the boundary of the frozen boundary is determined that is equivalent to a variational problem. And this was by Kohn. Okay, Kohn-Kenyon prop for lozenges and okay, at least for lozenges, and then Kenyon or Kunko-Sheffield for general diameter models. So we have this variational problem which describes, is satisfied by the scaling limit, the height function. We have the surface tension, which is in the general diameter model is of this form that the Hessian sigma is 1 plus some finite number of Dirac masses. But I will look at those cases where we have no Dirac masses. So then the domains will be simply connected, and it's more simple to work. But like I said, we have some results for also for the general case and for the multiply connected cases. Okay, and then the sigma is strictly convex and piecewise linear on the boundary, so it fits perfectly with our machinery. Here's the lozenge tilings sigma, and you see it blows up here on the boundary. Okay, and what is then the liquid domain? Well, that's, I mean, if you look at these pictures here we have the fixed corner or different color, fixed color. So these are the corners of the polygon. I mean, it's the support of the sigma. And so the liquid domain is those values of in the domain where the limiting height function has values in the interior of this polygon. So the square in our case of domino tilings. And then we say that the boundary is frozen if the limiting height function goes to the boundary of the constraint when we go to the boundary of the liquid domain. And then the question is to understand the geometric properties of the frozen boundary. Is there any questions at this moment? Okay, but so now when you look at this, we recall what we have for the universal Beltrami equation. So we have perfect tools for this. But first we have to do some regularity for this limiting height function, because it's just it could be a measurable function, and it's the points where the gradient is in the interior of the polygon, there would be some measurable sets, and then you would have nothing. But we have, luckily, the work of Da Silva Savin, who showed that the liquid domain is always open, and also that the limiting height function is C1 in the liquid domain. And with this information, then we can start to use our machinery. This I will show in a, I mean, this is our goal. And so this Kenyon or Konkov, they showed this fact for some special class Losentz models. I think they proved this is an image of rational function, if I remember correctly. But anyway. Okay, and now because we have this enough regularity for the limiting height function, it's C1, so then we can look at the corresponding divergence equation, and it's satisfied in our liquid domain. And then we can recall our theorem. It says that in this setting precisely, we have this limiting function, height function f. It's composed of these three objects. And now this height function here, now it's a proper map, because we are looking at the limit, this liquid domain with frozen boundary for the timer model. So this property gives us also this one is a proper mapping. And then the whole composition is of course a proper map, and it solves this equation. So the boundary of the liquid domain is rational. And if it's as this, in general case, we have these Dirac masses for this surface tensor sigma. So then it's algebraic curve with a similar proof as here. But simply connected is the easiest, easier to explain here. Okay, so and then when we wrap this up, we have the following characterizations. At first, we have 4 different conditions. First condition, so we have a bounded and simply connected domain in the plane. And the first condition, it's a liquid domain with frozen boundary for some dimer model. Second condition, there's a solution to the universal Beltrami equation, which is a proper map from the domain to the disk. So this is what we're looking for. Then, of course, the third condition is this, that we have the solution to the Euler-Lagrange equation, and where sigma is a surface tensor for some dimer model. And this, of course, does the tautology. And then the fourth condition is that this holds only for the Losentz model. So this proves some kind of universality, that if you have a liquid domain with boundary for some dimer model, I mean, whatever dimer model you choose, it will be the frozen boundary for the Losentz model. So Losentz model already presents all possible geometries of liquid domains. Okay, and so we have proved that this C, D, and A, they imply the condition B. But the question is, how do we go from B to these frozen boundaries? Or how do we go to the Losentz? How do we go from this Beltrami equation to the Losentz model? And then here I briefly sketch what are the properties of phenomena we have here that gives this conclusion. So we assume that we have the solution to this universal. So here you see the word universal because it holds for every dimer model. So that's our motivation for the word. Now assuming that we use the word, so we assume we have a solution to this equation on a simply connected domain. The question is how to make it a liquid domain for the Losentz model. Well, first we take the lozenge model and this surface tension which has a triangle. We had a picture of it. Triangle for the support of the surface tension. And then it happens that so that okay, maybe I. So we can so this is the support for sigma for the lozenge model, and then sigma is 0 on all boundary lines. This is the simplest case. And if you have something more complicated like the square, then this h prime, you can calculate the degree of the h prime from the corners and possible discontinuities of the derivative of the sigma on the boundary. And here it is the simplest case, and here the structure function is conformal. So we can take the inverse. For other, we can have a similar equation for other diameter models, but then we have to take this structure function in the game more carefully. But now, so for lozenge model, this h prime is conformal, so we can play with that as we like. And then we have this formula for the height function, I mean the function f. But now, if we have the f itself, what we can do, we can take inverse of this relation. Namely, it turns out that this expression, when you take the Levy transform and this structure function f, in these inverses, this has as a function of the domain, this has it's a curl-free expression. So it turns out that it follows from the properties of this Levy transform. It's curl-free, so it is a gradient of something. And now when we look at what the gradient satisfies, from the definition of the Levy transform, it immediately follows that this H is a solution to this divergence equation. It's a solution to this equation. So from H we have the solution of Beltrami equation. From solution of Beltrami equation we have H. So they're completely matched. We don't lose any information when we take one picture or the other. Then this Levy transform was a harmonic function. And it turns out that it maps to the support of the surface tension, and that's a triangle here. And it turns out that that's actually this harmonic function, which is here, the f is, so this was conformal, this is harmonic, so this is still harmonic. We have the f as a variable, and it's the sum of these harmonic measures, precisely. And these pk's are the three corners of the polygon. So it's perfect matching. and here we now see that, so if you have a domain, let's say H is somehow like this. So there are these inverse images of this, so these three intervals, the harmonic measures, so they come maybe, I don't know, let's say somewhere here. And then what we have to build a polygon. So we use so-called frozen extension. So we put here some polygon in the exterior of the domain. Well, this is quite sketchy. And then we extend it. So we know the color of each of these arcs. It's a color of this given arc. And then we have put that corresponding color over here. What we only have to worry about is that when we have this extension, then the domain is bigger, boundary values change. So how do we know that the original boundary values on this boundary of the liquid domain are still the minimizer of the bigger domain? So here one has to be careful. And then we have to do the extension so that so-called minimal and maximal extension of this boundary values to this bigger domain, they are the same. And then there's no problem. That requires some combinatorial stuff. And then it doesn't work for every polygon, but for lossless model and triangle, it works fine. So that saves us. Okay, so I have, okay, let me just, I was planning not to give the last slides, but maybe it's, do you want to see it or? Yeah. Okay, so question, what kind of rational functions we get? So we saw that these liquid domains with frozen boundary, they are rational. Boundaries is rational, parameters by rational function, but what kind of rational function? And it turns out that here we have some at least almost explicit information, not let's say semi-explicit. So we have this rational. I mean, we have rational function parameterize this kind of liquid domain frozen boundary if and only if these three conditions hold. So first of all, we have a Plaske product, because I mean that's how the machinery was built with. And then the first condition that this rational function is univariate in the close to the boundary of the unit circle. So that means that so if you like look at like this function, so it maps to something like that. So it's injective here in the interior, but not in the exterior. It's, I mean, it takes these sides and put them together. So in the interior it's injective, but then in the exterior it will lose injectivity. So that kind of univalence is required. And then we have these invariance properties with the Plaske product and the rational map, which are these two conditions. Then in principle, if you have your Plaske product, you can calculate what kind of liquid domains you can have. And I just took like the first ellipse is a good example. This is the Plaske product, and it satisfies this condition. So ellipse is one of the liquid domains. And then there's polynomials here with this polynomial Plaske product and rational map, and so on. So thank you for listening.